This section introduces the single reversal. The whole book turns on. Stop fitting a function, f from x to y in the forward direction. Posit instead a generative process, a prior p of z times a likelihood p of x given z, and invert it, recover the hidden cause, the posterior p of z given x, from the observation. That one reversal is the book's spine. Pearl called forward, fitting, glorified curve, fitting, and it predicts the pattern. A model-based approach recovers the latent structure generating that pattern, the way the scientific method posits a mechanism behind the data. The 4 tasks the book organizes: prediction, generation, discovery, and control are all this same inversion taken to different depths, formalized as Bayesian inference over probabilistic models. The sleight that does the real work hides in the footnote. Inference here means running a function backwards to its causes. The deep learning sense of the word means applying a function forward. Same word, opposite direction, and the whole argument rides on which one you mean. This section names the single primitive that underwrites the entire book. Name the process that generated the data as a probability distribution. Then invert it, working backwards from observations to hidden causes. That inversion is the whole move. Every task Murphy will spend 6 parts on is that same object, queried differently. Prediction asks for the probability of y given x. Generation asks for the probability of x. Discovery asks for the probability of z given x. Control asks which action bends the distribution best. The surprise that makes the book worth reading hides in a footnote. Deep learning inference merely runs a function forward. Bayesian inference does the harder thing, running the arrow backward. So Pearl's phrase, glorified curve fitting, and the understanding the book chases differ only by direction of the arrow. The 4 tasks are 4 questions put to one model. This section explains probability as a single primitive, a measure that integrates to one, that is the whole of it. Fix a sample space, call it omega, together with the sigma field of admissible events. Assign each event a weight between 0 and 1, that is additive over disjoint pieces and sums to 1 on omega. The so-called axioms are just the measure, axioms with total mass fixed. A random variable adds nothing new. It is a push forward, relabeling that same measure onto the real line through pre-images, giving the probability mass function or the probability density function. Conditioning is renormalization onto a subset. Bayes is that same renormalization read backwards. The discrete and continuous cases split only on whether the sigma field is enumerable or Borel generated, sum versus integral, one object. The rest of the book rides on this single primitive. This section explains the single structure that generates all of probability. One structure generates the whole subject, the triple written as capital Omega, a sigma algebra called script F, and a measure called capital P. Capital Omega holds the outcomes, script F is a sigma algebra of events, and the measure sends each event to a number in the interval from 0 to 1. A random variable is a function from capital Omega to the real line called capital X, and its work is to push that measure forward onto the real line. The probability mass function, the probability density function, and the cumulative distribution function are 3 views of that same transported measure. Conditioning, independence, and Bayes then fall out as arithmetic on capital P. Bayes is just the multiplication rule read backwards. The chapter's move is to axiomatize the measure rather than the distributions, and to let every distribution be its shadow. Everything the rest of the book infers is bookkeeping on this one object. The density is downstream, never foundational. This section explains what separates probability from statistics and how that single split forces the two schools of inference apart. Probability runs the arrow forward. You fix theta, distribute over the data, and compute the probability of the data given theta. Statistics inverts it. You fix the data you actually saw, distribute over the parameter, and recover the parameter, and recover the probability of theta given the data. That single inversion of the conditioning bar is the whole chapter's seed. The two schools it branches into differ on one question only: where is uncertainty allowed to live? The Bayesian lets it live on theta. Parameters are random, the dataset is the one you have, and the posterior is the answer. De Frequentis forbids that, pinning theta fixed and putting all randomness on hypothetical repetitions of the data. Choose which side of the bar carries the distribution, and every later construction is forced. Priors, estimators, confidence versus credibility. This part explains why inference is inversion. Statistics is probability run backwards. Chapter 2 gave you the forward map. Parameters theta generate data through the probability of the data given theta. This chapter inverts that map, recovering theta from the data it produced. That inversion is ill-posed. Many values of theta explain the same data. D, so the inversion needs a regularizer. The prior, the probability of theta on its own, is exactly that regularizer, the belief that disambiguates among the competing explanations. Bayes' rule is the whole content. The posterior probability of theta given the data is proportional to the prior probability of theta times the probability of the data given theta. Everything downstream is a corollary of reading. A generative model in reverse, MAP estimation, maximum likelihood as the flat prior limit, and conjugacy as inversion that stays inside one family. The chapter's job in the book is to establish that inference is inversion. Once that lands, every later method is one more way to run a model backwards. This section explains what a graphical model buys you and why. A joint distribution over n variables costs order, k to the n power, every configuration priced separately. The whole move is this: read off which variables are conditionally independent, and the joint splits into a product of small local factors, one per variable given its parents, collapsing the cost to something sparse. A graphical model is just the ledger of those independences drawn as a graph. Murphy notes the honest name is independence diagram. The missing edges carry the content, not the nodes. This is Jordan's pair, factorization meaning modularity and averaging meaning abstraction made into a picture. Predict the rest from there. A denser graph means weaker savings. Fully connected, there are no independencies, and the model buys you nothing. This section explains why a single graph can stand in for a joint distribution over many variables. A joint distribution over many variables is intractable. Head on, k to the n, configurations to name. The move, let a graph be the factorization. Every absent edge asserts a conditional independence, and the whole distribution collapses into a product of local factors, one per node given its parents. Sparsity turns exponential cost into linear, times a small power. Structure does real work here. The graph is the list of independence assumptions, Jordan's two levers, factorization and averaging, made drawable. Murphy's own aside makes the point these should be called independence diagrams rather than graphical models. What the picture encodes is precisely what you left out, the edges you declined to draw. This section explains information theory as a single structural idea seen from many angles. Information is the size of a belief update, how far new evidence moves you from a prior, call it Q, to a posterior, call it P. Murphy's move is to show that a short list of desiderata, continuity, non-negativity, permutation, invariance, and monotonicity on uniforms forces a unique measure, the KL divergence. Invariance, the KL divergence. ARI, entropy is KL against the uniform. Mutual information is KL between a joint distribution and its marginal product. The two applications, compression and error correction, are the same primitive turned operational. Both need an accurate probabilistic model, one to shorten frequent code words, the other to infer the likely source through noise. The inversion is the surprise. KL is the primitive, and entropy is the special case. This part explains how a short list of requirements pins down a single measure of belief change. The requirements are these: continuity, non-negativity, permutation invariance, monotonicity on uniforms, and a chain rule under partitioning. Together, they fix a unique measure of how far one belief has moved from another, the KL divergence. That is the whole chapter in one move. You define the quantity by the properties it must obey, and its form crystallizes, with entropy and mutual information falling out as special cases. Both engineering payoffs, compression, and error correction, then reduced to the same thing, possessing an accurate probabilistic model. The generative primitive is the axiomatic one. An object is what it must satisfy. So information is the measured magnitude of a Bayesian update, the size of a move from one belief to the next, with no existence as a stored substance. This section gives the shape of the whole optimization chapter. Every method here wears one template. Theta star lies in the arg-min of the loss, L of theta. The real content is the manufacture of the gradient, what you do when something blocks the naive derivative. The descent rule itself carries little of the interest. There are 4 obstructions and 4 moves. Composition depth yields to automatic differentiation, the chain rule made mechanical. Stochasticity inside the objective yields to unbiased estimators, the score function estimator, and reparameterization. The parameter space's own curvature yields to the natural gradient, descent in the metric the distribution induces rather than in raw coordinate, descent in the metric, the Trivesi, inside the overbound, Ald over Rauers, all double yields to EM, ascent on a lower bound. The unifying surprise is that you never optimize L directly. You optimize a faithful surrogate of its gradient, and each section is one obstruction dissolved. This section explains what makes every learning problem in the book actually run. Every such problem is a single line. Theta star lies in the set of arguments that minimize L of theta. This chapter is what makes that line execute for objectives of any shape. The move that makes it go through is treating differentiation as an operator on functions rather than as a matrix of numbers. The derivative operator maps a function to its derivative function, and because applying it twice is the same as composing it with itself, derivatives compose exactly as the functions do. So the gradient of an arbitrarily deep composition is never materialized. It is applied as a chain of Jacobian vector products or vector Jacobian products. That single reframing is the chapter's gift to the rest of the book. Fitting is minimization, and minimization is executable because the chain rule is compositional. This section explains why 7 inference algorithms are really one problem, wearing 7 faces. Every unknown, a prediction, a hidden state, a parameter becomes a random variable. An inference is a single operation. Compute the posterior by conditioning on data. Bayes' rule makes the numerator trivial. The whole difficulty collapses into one high-dimensional integral, the normalizer, which is the probability of the data, together with the expectations that integral, the normalizer. So the 7 algorithms are one problem, seen through the menu of ways to evaluate that integral. The evaluation is exact when the prior and the likelihood are conjugate, approximate otherwise, and each method is sorted by the trade-off. It accepts among speed, accuracy, and generality. Here is the primitive to carry. Integration is to inference what differentiation is to optimization. And because the machinery is model independent, you build the best model and hand the rest to an inference engine, turning the Bayesian crank. This section explains why the whole of Bayesian inference reduces to a single hard object. Every unknown becomes a random variable, and inference then collapses to one operation: divide the joint probability of theta and the data d by its integral over theta. That integral, the normalizer z, is the entire difficulty. Nothing else genuinely resists. So this chapter functions as a map. Rather than delivering a method, it sorts everything downstream by how each algorithm attacks z. Where optimization lives on differentiation, Bayes lives on integration, the dual that organizes the whole. And because the integral is model agnostic, you build the model, then hand it off, what Chapter 7 calls turning the Bayesian crank. 3 latent geometries, global, local, and both, generate the algorithm families to come. This section explains Gaussian filtering and smoothing at the structural level. Picture a running belief about a hidden state, held as a Gaussian, marched along time by alternating 2 moves. First, predict. Push the belief forward through the dynamics. Then update. Bend it toward the newest observation by Bayes. The whole chapter rests on one closure fact. A Gaussian survives both a linear map and conditioning on linear. Gaussian evidence, so the belief never leaves the family and inference stays closed form. That recursion is the Kalman filter. A backward pass over the same fixed points gives smoothing. Every named variant, the extended and the unscented, is the identical 2-step, differing only in how it forces a nonlinear model back into a Gaussian. Predict, then correct, forever within one family. Where the family breaks, you approximate. This section explains why keeping a belief Gaussian turns inference over a whole hidden trajectory into a fixed-size recursion. Keep the belief a single Gaussian, and inference over an entire hidden trajectory collapses to a fixed-size recursion. Each step folds one new observation into a running mean and covariance, never revisiting the raw history. That closure is the whole chapter. Linear Gaussian dynamics take a Gaussian in and hand the Gaussian out, so the Kalman filter is Dyson in and hand the Gaussian out, so the Kalman filter is just Bayes' rule applied once per time step. Filtering conditions on the past alone, the probability of the hidden state at time, to given all observations from the first up to time t. Smoothing adds a backward pass, so the future revises the past. Think of Murphy's detective, whose late clue renders every earlier confusion obvious in hindsight. Here is the step that does the work. Conjugacy makes the belief self-similar across time, turning an unbounded history integral into constant cost updating. This section explains what message passing algorithms are at their core and the single condition under which they stay exact. Inference on a graphical model is dynamic programming. Wearing a graph as its recursion structure, the intractable object is a joint distribution over many variables. It factorizes along the graph's edges, and that factorization means the global sum or the global maximization decomposes into local subproblems whose solutions you cache and reuse. A message is exactly one such cached subproblem. It is a node's belief about a neighbor, summarizing everything on one side of the graph. Pass the messages, let every node combine what arrives, and the marginals fall out without ever enumerating the joint. Here is the constraint the chapter builds toward, the step everything else depends on. This is exact if and only if the graph is a tree. The recursion needs an unambiguous order in which to solve its subproblems, and a cycle destroys that order. This part explains why inference on a graphical model is really one familiar algorithm in disguise. Inference on a graphical model is dynamic programming, wearing the graph as its recursion tree. That is the whole chapter compressed. Conditional independence from Chapter 4 means a global marginal factors into local quantities, and the graph's edges tell you exactly which subproblem feeds which. So each node computes locally and ships the result to its neighbors as a message, itself a belief state, a distribution over that node's value given one slice of evidence, until every node agrees on the global answer. The chain is the atom. Sweep beliefs forward, then backward, and combine. Chapter 8's Bayes filter is this same sweep. Trees, then loopy graphs are just the same move on richer connectivity. The topology is the algorithm. This section explains variational inference at the structural level, the move that turns an impossible integral into an optimization you can actually run. Posterior inference asks for an integral you cannot do. The evidence, the probability of x, which equals the integral over z of the joint probability of x and z. Variational inference refuses the integral and searches instead. You pick a tractable family Q, then slide its parameters until Q sub psi sits closest. In callback, Leibler divergence to the true posterior until Q sub psi sits closest in. The trick that makes this run is that the intractable evidence, though present in the divergence, is constant in psi. Drop it, and what remains is a computable objective, the E-elbow, a lower bound on the evidence whose slack is exactly the divergence you wanted to kill. Maximize the bound, and you close the gap. The chapter compresses to one line. Inference becomes optimization. Murphy gives you the same object twice, the evidence lower bound of statistics and the variational free energy of physics, differing only by a sign. This section explains how inference turns into optimization. Inference becomes optimization, that is, the whole chapter. The posterior, the probability of the hidden variable z given the data x, needs a normalizing integral you cannot compute. So you stop computing and start searching. Pick a tractable family, Q. Then find the member Q closest to the true posterior in KL divergence. Here is the move that makes this pay. The KL divergence from Q to the true posterior P equals the elbow plus the log evidence, that is log P theta of x. The intractable evidence term is constant in your parameters, so minimizing the part you can evaluate, the elbow, or in the physics framing the variational free energy, drags down the divergence framing the variational free energy drives down the divergence you cannot. Everything after is choosing Q, rich enough to sit close, cheap enough to optimize. That is the single tension the rest negotiates. This part explains why Monte Carlo integration exists and where its one surprising property comes from. An integral is an expectation, and an expectation is a long-run average. So, to compute the integral of f of x times p of x dx, you need not grid the space. You draw samples x sub n from P, and you average f over them. The single structural surprise is that the error is indifferent to dimension. By the central limit theorem, it shrinks as sigma over the square root of n, a rate set by the sample count alone, not by how many coordinates x carries. That indifference is the entire reason the method exists. Grid quadrature dies exponentially in dimension. Monte Carlo does not. The difficulty does not vanish. It relocates. You must now generate draws from P, and in high dimensions that is itself the hard problem, the one that chapters 12 and 13 on Markov chain Monte Carlo and sequential Monte Carlo are built to solve. This section explains the single move at the heart of Monte Carlo integration. An expectation is an integral you cannot do. A sample mean is one you can. That single swap is the whole chapter. Replace the integral of f of x times p of x with respect to x with 1 over n times the sum over n of f of x sub n, where each x sub n is drawn from P. The surprise that shifts your prediction falls straight out. The error shrinks as 1 over the square root of n, no matter the dimension. So sampling walks straight through the curse that strangles grid integration past 3 acts. Everything downstream is 2 sub-problems. First, how to draw x sub n from P by inverse CDF, by rejection, or by importance sampling. Second, how to shrink the estimator's variance by Rao-Blackwellization, by control variates, or by antithetics. This is the primitive toolbox of the book's inference arc. Chapter 12's MCMC and Chapter 13's SMC are its extensions to the high-dimensional regime where naive drawing collapses. This section explains Markov chain Monte Carlo, the sampling engine of Part 2. You cannot draw from a high-dimensional target directly, so invert the problem. Instead of sampling the target distribution P star, build a dynamics whose equilibrium is P star. Then simply let it run. A Markov chain, a memoryless random walk, forgets its starting point into a stationary distribution. Markov chain, Monte Carlo engineers the transition rule so that fixed point equals the target. Sampling becomes fixed. Point construction. The long-run fraction of time. The walk spins in each state, then equals its probability there. Ergodicity converts a time average into the integral you wanted. That is the chapter's whole move, and Part 2's engine. Do not compute the distribution. Construct an operator that leaves it invariant and run it to stationarity. This section explains how Markov chain Monte Carlo makes an impossible sampling problem tractable. Sampling from a distribution you cannot even normalize becomes tractable the moment you stop trying to sample it directly and instead engineer a process whose equilibrium is that distribution. That is the whole chapter. Build a Markov chain on the state space whose stationary distribution is the target, P star, run it, and let the fraction of time the walk spends in each state, P star, run it, and let the fraction of time the walk spends in each state be your sample. The hard problem drawing from P star is never solved. It is dissolved into the fixed point of a dynamical system you design. Chapter 11's independent drawers collapsed in high dimensions, and the price of survival here is correlated samples. The subsuming primitive convert an intractable object into the attractor of a process.